I'd like to show you a new concept, which is the extended phase space. It's actually something we've already used when we discussed the action principle in phase space. It is the phase space, the 2f dimensional phase space, with one added dimension, which is the time axis. So if we have a one-dimensional system, then extended phase space looks like this. We have Q and P, the phase space coordinates, and then we have a third dimension, which is time. Now at each time, the system is in a certain state. Say at time t equal to 0, we have the initial condition that the system is somewhere here. And then as time evolves, we move to the right along the time axis, and the system moves also in phase space. So it will move along some trajectory in this extended phase space. So here we have the, in general, it's the 2f dimensional phase space here, and then plus the time coordinate. So extended phase space is 2f plus 1 dimensional. Let's say this green trajectory is indeed the physical trajectory of our system. And what we could do is we could project this motion onto the ordinary phase space. So we could say that initially the system was here in ordinary phase space. So this is again Q and P. And then at the end, the final time, let's say the system is here, and in between there is some motion. So we have Q as a function of t and P as a function of t as a trajectory in ordinary phase space. So it's basically the projection of the trajectory in extended phase space onto the regular 2f dimensional phase space. But let's look now at the extended phase space, and let's take at some point along this physical trajectory, let us look at the tangent vector. Let me call this tangent vector W. What are the components of that tangent vector W in extended phase space? Well, it's the time derivative of the position vector in extended phase space. The position vector in extended phase space has 2f plus 1 components. The first 2f components are simply the q's and the p's, and the last component, the additional component, is time. So when I take the time derivative now of that position vector, I get W. And I first have the q dots, then I have the p dots, and then in the last entry I have the time derivative of t, but that is simply equal to 1. Here I gave the vector just in one dimension, so I can do without the indices. I just have one q dot, one p dot, and I have 1. Since this is the physical trajectory, the Hamilton equations must hold, and therefore it must be true that the q dot is equal to the partial derivative of the Hamiltonian with respect to p. P dot is minus the partial with respect to q, and 1 is 1. Now we look at so-called tubes in extended phase space. These are the axes of extended phase space. So here again we have T, Q, and P. And let's look now not just at a single physical trajectory, not just this one here, but with the initial condition as I drew here. That's the left dot, that's the initial condition at t equals 0. Let's look at several different initial states. And these initial states are all located on a loop, on a closed loop. So this here is a closed loop of initial states at t equals 0. So as for the point that I drew on this loop, the physical trajectory looks as you see on this graph. We can take another point on this loop as our initial condition, and that will evolve on a different physical trajectory. It might look like that here, and this point might evolve on this trajectory, that point here on another trajectory, and so on. So these are all physical trajectories. After some time t, these initial states will all have evolved into certain final states. And the final states will also lie on a loop. So there will be some loop of final states, also a closed loop of final states. This loop will generally look different, maybe deformed in some way. It certainly has a different position in phase space, but it's still a closed loop. And what you see from this picture is when you start from this initial loop, and then you look at the physical trajectories, and this evolves into a final loop. The physical trajectories, they cover the surface of a tube. So these physical trajectories, they cover a tube. And then we can say that this area enclosed by the initial loop, that is the bottom of the tube. The area enclosed by the final loop, that is the top of the tube. And then here we have the side of the tube. As before, we can consider tangent vectors to these physical trajectories. So we can consider, for example, here, we can consider the tangent vector W. At this point here, we can consider the tangent vector. Here we can consider the tangent vector, and so on. And they form a vector field. So vector field. and that is composed of the, or is generated by the physical trajectories. And remember the components of this tangent vector, that was the partial h with respect to p minus the partial with respect to q and 1. Now, a first observation about this vector field is that its divergence vanishes. The divergence is given by nabla in this extended phase space, scalar product with the field W. So what it is that? It's the partial with respect to Q of the first component of W, but the first component of W is the partial of H with respect to P. Then we have the partial with respect to P of the second component of W, but the second component of W is minus dH over dQ. And then we have the partial with respect to T of the third component, and the third component of W is 1. And you see that these two terms cancel. The partial derivative of 1 is equal to 0. So the divergence is equal to 0. So this is one first observation when we consider these physical trajectories in extended phase space, that they are tangents. They define a vector field, and the divergence of that vector field is equal to 0. Now this has interesting consequences. Let me quickly sketch this tube again. And here we have the vector field W. Then the theorem of Gauss says that when we take the surface integral of a vector field W, we take the surface integral over a closed surface, and as the closed surface we choose the surface or the boundary of the tube. That's the boundary of the tube. Then by the Gauss theorem, this is equal to the volume integral over the interior of the tube. The volume integral of the divergence of W, but the divergence we just showed to be equal to 0. So consequence of that previous result is that the surface integral over the surface of the tube of W vanishes. When we take the surface integral, we always have to take into account the orientation of the surface. So it's important to keep in mind when you have the tube here, we take the surface integral, then the surface has an orientation, and this orientation is pointing outwards. So here it's pointing to the right, here on the sides it's pointing perpendicular to the surface, and here at the bottom it's pointing to the left. And what we can do is, we can, as for the bottom, we can define a vector pointing in the opposite direction. Let me call that df prime. This is simply minus df, so that at the bottom we also have a vector pointing to the right. Now let's look at this surface integral. This surface integral over the surface of the tube, that can be decomposed into three parts. The surface of the tube is composed of the side of the tube, the bottom of the tube, and the top of the tube. Now the integral over the side of the tube will not contribute, because the vector field omega by definition is tangent to the side of the tube, and the oriented surface vector is perpendicular to the surface of the tube, and therefore the scalar product vanishes. So this one here does not contribute because W is tangent to the side, and therefore there's no flux through the side, and the scalar product is equal to 0. So what remains then, since we know the surface integral must be 0, and only bottom and top remain, we find that the integral over the top of df, the flux through the top of W, must equal minus the flux through the bottom. But this we can also write, if we use, for the bottom, we use df prime rather than df, we can write it as equal to bottom df prime W and so this is our result here, that the flux of the vector field W through the bottom equals the flux of the vector field through the top. So the flux or the flow of this vector field is conserved. To simplify the discussion, I'm now focusing, have already been focusing on the one-dimensional case. First, because I can, in the one-dimensional case, I can draw extended phase space. It's then three-dimensional. And I don't have to carry the indices. And there's one further simplification, because in 3 dimensions, if the divergence of a vector field vanishes, then you know that you can write this vector field as the curl of another vector field. That's what I would like to do next. We know that the divergence of W is 0, and therefore there exists another vector field, and let me call that capital X, such that W can be written as the curl of that field X, and just by convention I would like to introduce a minus sign, so I say this is minus the curl of X. let me give you this vector field X. This vector field X has components in extended phase space P, 0, and minus the Hamilton function. We can check that minus the curl of X. This is minus. And then we have, for the first component, we have the partial with respect to the second component of the third component of the vector field X minus the partial with respect to the third component of the second component, which is 0. Then for the second component of the curl, we have the derivative with respect to the third component of the first component minus derivative with respect to the first component of the third component, and here finally derivative with respect to the first component of the second component minus derivative with respect to the second of the first. And you see indeed the first component minus the partial of h with respect to p, and then a total minus sign in front gives the partial of h with respect to p. For the second component, the partial of p with respect to t vanishes. There's no explicit time dependence of p. And what remains is minus the partial of h with respect to q. And then finally, the last component, the only term that contributes, dp over dp, this is 1. And that is indeed the vector W. So we have this new vector field X. This allows us to formulate a new invariant of the dynamics. Let us consider the top of the tube. So we have the physical trajectories arriving here. This is the top of the tube, and we have here our vector field W. Our vector field W, we have the surface vector df. So we have the flux through the top of the tube, df scalar product with W. W is minus the curl of x. So this is minus the integral over the top of the tube df and then the curl of x. And then we can use Stokes' theorem, which says that the flux through an area equals the line integral along the boundary of that area, around that area. So this is this area integral is the line integral around the closed loop of this vector field capital X. And this vector psi that I introduced here, that is a position vector in extended phase space. So we have this line integral around the closed loop due to Stokes' theorem. What is that scalar product d psi with x? D psi, that's sort of an infinitesimal distance vector in extended phase space, and it has the components. It has the components dq, dp, and dt. And we take the scalar product with the vector x, and the vector x had the components p, 0, and minus the Hamilton function, minus h. So that scalar product gives us p dq minus h dt. So here we have an expression for the flux through the top of this vector field W. We had seen that the flux is conserved. So the flux through the top equals the flux through the bottom. The flux can be written as this loop integral. So it must also hold that this loop integral must be the same around the initial loop and the final loop. So the loop integral of p dq minus h dt is an invariant of the motion. It must be the same for the initial loop and for the final loop. And this invariant loop integral has a name. It's a Poincare-Cartan invariant. This result allows you to understand many fundamental properties of classical mechanics very elegantly, much more elegantly than with conventional methods. So it's a very useful invariant. I should add that the loops, both the initial loop and the final loop, they don't necessarily have to be simultaneous loops. So in the sense that all points on this loop belong to the same time. But I'll come back to that in a second. What we had shown was that this loop integral was invariant. And we had shown that for the one-dimensional case. I will tell you without proof that when you generalize this to higher dimension, then the invariant becomes sum over I pi dqi minus h dt is invariant. And this is for arbitrary dimensions called the invariant of Poincare and Cartan. The Poincare-Cartan invariant helps us determine how the Hamilton function changes, is modified when we do a time-dependent canonical transformation. So let's consider the starting point, the Poincare-Cartan invariant is this loop integral sum over I pi dqi minus Hamilton function dt. And let's now perform a canonical transformation going from little coordinates to capital coordinates. This canonical transformation is generated by some generating function g, and now we allow the canonical transformation to be time dependent, and we implement that by allowing the generating function to be time dependent. So we have the transformation generated by a time dependent generating function g which is a function of the old and the new position coordinates, and now depends also on time. It's still true that the old momentum, little p, is obtained from the generating function by taking the partial derivative with respect to little q. Then let's look at the Poincare-Cartan invariant. And let's, for simplicity, stick to one dimension so I don't have to write the indices. And so we start from p dq minus Hamilton function dt. We express the little p, the momentum, as partial of g with respect to q dq minus Hamilton dt. Now the differential, the total differential of the generating function, if it is time dependent, has the form that we have seen before, partial derivative with respect to little q dq plus partial with respect to capital Q d capital Q. But now it gets an extra contribution that comes from variation of time. So we have a partial derivative with respect to t dt. We can solve that relationship, that equation, for the first of these three terms, so for the partial of g with respect to little q dq, because that's what appears in the integrand of the loop integral. And then but then we can also exploit that the loop integral over a total differential is always equal to 0. And then this takes the following form. Well, we replace the first term in the integrand by, with the help of the total differential of dg minus the other terms. Loop integral over the dg vanishes, and all we have is minus partial g with respect to capital Q dq minus partial g with respect to time dt minus Hamilton function dt. But we know that minus the partial derivative of the generating function with respect to the new position coordinate, capital Q, that this is the new momentum coordinate, capital P. So this is in fact capital P dq. Then we have two terms, both proportional to dt. Let's group them together in a bracket, and let's write this as minus Hamilton function plus the partial of the generator with respect to time dt. Now you see that when you go to new coordinates, this Poincare-Cartan invariant has the same form. It's again p dq, now in the new coordinates, minus some function times dt. And this function in front of the dt now takes the role of the new Hamilton function. So this has become now h prime. This is the new Hamiltonian. This tells you the transformation rule for the Hamilton function, when you have a time-dependent canonical transformation generated by a time-dependent generating function g, then the Hamilton function must be modified. The new Hamilton function h prime equals the old Hamilton function h plus the partial derivative of the generating function with respect to time. This is the transformation rule for the Hamilton function. We showed that the Hamilton equations of motion lead to this Poincare-Cartan invariant. You can also show the reverse. You can say when you have some evolution and there is a Poincare-Cartan invariant, then this means that the evolution is governed by Hamilton equations of motion, where the Hamilton function is the function in front of the dt. Given that, we have now seen in the new coordinates, we still have a Poincare-Cartan invariant. So in the new coordinates, we still have a motion governed by Hamilton equations of motion, with the Hamilton function being the function in front of the dt, which is this modified h prime. So here once again I wanted to make this remark that the initial loop and the final loop, they don't have to be on the same time. So the points on that loop don't need to have the same time coordinate. Let me take, for example, a slice here at fixed time, and then we get a cut like this, and the final loop, however, need not lie on this surface of constant time. And so we allow this invariant loop integral applies to arbitrary loops around the tube, and the loops don't have to be at any fixed time. But then, of course, we have the situation where the loops do lie on slices of fixed time, and these are simultaneous loops. So if we do require that these loops all are at a constant time, then, of course, this invariant loop integral then the dt is equal to 0 if we are at constant time. And then this invariant becomes simply the sum over I, and then this loop integral pi dqi. And then we find, when we restrict ourselves to simultaneous loops, we find that this expression in the box, this loop integral, is a constant of the motion. But this observation implies that, in fact, evolution is governed by a canonical transformation, or can be understood as a time-dependent canonical transformation, for the following reason. Let's draw again the picture in extended phase space. And let's say you start initially at some position in phase space with coordinates q naught and p naught. This evolves in time, in extended phase space, and then after some time t, you have position q of t and momentum p of t. And formally, we can consider the map from the original location in phase space, from the Q0 to P0, to the new position, the new location in phase space, the Q of t and P of t. We can say, we can give these new symbols. So the Q0s and P0s we identify with these of the original coordinates, little q, little p, and the position or the location in phase space at some later time we view as the new coordinates, and we call them capital Q and capital P. And we consider this map from the original to the new coordinates as a coordinate transformation in phase space. We just learned from the consideration of simultaneous loops, we learned that the loop integral, that's the loop at time 0, PdQ, is a constant of the motion, so it's the same as the loop integral at some later time t of the PdQ, which we now denoted by capital letters, PdQ. But now remember, we had shown earlier today that we can view the conservation of this loop integral as a criterion for a transformation being canonical. So that's an alternative way of characterizing canonical transformations. We can take that as the defining property, an alternative defining property of a canonical transformation. So since the loop integral is conserved, this coordinate transformation must be canonical. Right? Well, this implies that the coordinate transformation is canonical. So this is one more argument or one more indication why canonical transformations are so important in classical mechanics. They appear everywhere. And in particular, you can view time evolution as a time-dependent canonical transformation. Now you might ask a very interesting question. If the time evolution can be viewed as a canonical transformation, and every canonical transformation has a generating function, you may wonder, what is the generating function of time evolution? It turns out, and we will discuss that later in the context of Hamilton-Jacobi theory, that the generating function for time evolution is the action. Now this is a subject of Hamilton-Jacobi theory, and we'll do that later. This may perhaps answer in part questions that you've asked before. How can we, or what interpretation, physical interpretation can we give to the action, to the Lagrange function, to the Lagrangian? Up to now, we have viewed the action as the functional that is minimized by a physical trajectory. Here, the action acquires a new meaning, an additional meaning. It's the generating function of the canonical transformation that describes time evolution in phase space. But as I said, this is just an outlook for Hamilton-Jacobi, and we'll come back to that. This observation that time evolution can be viewed, can be regarded as a time-dependent canonical transformation has, amongst others, one important consequence, and that is the so-called Liouville theorem. The logic is very simple. We say time evolution is, in fact, can be viewed as a canonical transformation. Secondly, we know that canonical transformations preserve phase space volume. Taken together, this means that time evolution preserves phase space volume. And this statement that's Liouville's theorem. Phase space volume is conserved. So when you picture this in now just ordinary phase space, not extended phase space, ordinary phase space, you have an initial volume, and you have initial conditions somewhere all over this volume. Say you have this initial condition here, and there, and there, and so on. And you get final states, and the final volume is the same as the initial volume. Now I promise to you, and this is really going to be the last statement of today, I promise to you to give you just a little bit an idea of the physical meaning of phase space volume. And you can only fully understand that when you have some background in quantum mechanics. But the qualitative statement is that the phase space volume is related or can be regarded as the number of states. It's related to the number of states. So phase space volume is up to a prefactor. It's proportional to the number of states. A more precise statement is that the phase space volume, which I'll denote by omega, is related to the number of states by a factor 2 pi h bar to the power f, where f is the number of degrees of freedom, times n, which is the number of states. So the fact that under time evolution phase space volume is conserved, you can interpret that physically as the statement that the number of different states is conserved under time evolution. That's a result that will play a role later in statistical mechanics. So here you have an important link to statistical mechanics and also to quantum mechanics.